Hi, we are Group 5 of Digital Electronic Design, and right now we are doing Lab 2. And I'm Gong, this is Li Zhi, and this is Shin. So we'll begin our lab now. Thank you.
For right now, we are doing part 1 of the Lab 2 project. As you can see here, we are using the S74 HC74D type flip-flop for this part 1. And before that, we have to set SD and RD to high so that it will not affect the circuit operation. And now I will explain how does it work in the prototyping board. For D, as you can see here, we set it to high, and clock is low input, we get no input. And at the rising edge of clock, we set it to high, we get 1 input. And for this part, when clock is low and D is high, we get high input. And for this part, clock is low and D is low, we still get 1 input. And at this rising edge, when clock is high and we get no input. And after that, for this whole part, we get low input because D is low input, and low input. And clock when it's low and D is high, we get no input. And at this part, clock is still low and D is low input, we still get no input. And at this part, D is 1 input, but clock is still low and we get no output at all. And at the last part, when D is high and at the clock of the rising edge, we get 1 input. Right now we are doing part 2 of Lab 2 project. So by looking at the Q output, we should get this type of output. And after we connected the prototyping board to the oscilloscope, we can see that we get the output same as the expected output. So right now we would like to find the expected waveform, which is 250 kilohertz by calculating using the formula. And in the oscilloscope, we also get the expected value of the frequency, which is 250 kilohertz for channel 1, which is the output value. And for the input value, we set the clock to 500 kilohertz, which is required for this part 2 project.
Required to count from 1 to 6 using the 161 for synchronous counter. So this is the truth table and this is the Boolean equation. So we're using 161 4-bit synchronous counter and connect to 2 input NAND gates. So this is the schematic diagram with the pin numbers, and this is our board, shortcut board. And using the 1 kilohertz, and this is the input. So when we start our input, so this is the output. So as you can see, we're starting from this one 001 to 110, which is 1 to 6, and so 001 10 01 01 start all the way to the 001 010 011 100 101 and 110.
For part 5, we are doing the combination of part 3 and part 4. And in this part 5, we are required to roll a dice, and this is the table that we obtained by by combining part 3 and part 4. And this is the K-map that we have done. A is equal to Q0, B is equal to Q1, Q2, C is equal to Q2, and D is Q1 plus Q2. And this is the schematic diagram that we have drawn on the paper. And let's just demonstrate on the circuit board. By pressing this input, and the dice will become from 1 until 6. 1, 2, 3, 4, 5, 6. So we can prove that our circuit is working normally. The frequency that we are using for the dice is 1 Hz, and if we are using 1 Hz of frequency, the dice will slowly changing from one number to another number. However, if we change the frequency of the circuit board, there will be some differences for the dice. Let's see if we are using 2 Hz of frequency. The dice changing to another number is faster. Let's try for 10 kilohertz. 10 kilohertz, yeah. Let's see the dice. Oh, we cannot see the dice. Okay, I will reduce the frequency to 1 kilohertz. Okay, still not working. Okay, never mind. Yeah, so the frequency we're using is 20 Hz, and this is how it looks on the die module. If we want to obtain a number by using 20 Hz frequency, we have just to start let the dice to roll, and then just release the button, and we get the number. Yeah, the number that we obtain is time. Why? Okay. For the next number, if I release the button, we get 3. So we can prove that our board is doing perfectly.